Okay, so in this session we're going to start with an overview of hydrology. Hydraulics of structures will follow after that, and then open channel flow. Now, I would think if those in the audience have an ag engineering degree, some of what I'm going to cover would have been covered within Ag classes, and some would have been covered within civil engineering classes. It just depends on where you took your undergraduate work, uh, how much it's distributed across those two um, departments. So within the hydrology, the basic stuff that we're going to cover is first an overview of the hydrologic cycle. Then we'll get into some of the details of precipitation, specifically how to figure an average over an area, and then the concept of return period, which is really important when you get into design of structures. Then we'll talk about abstractions from rainfall, essentially where does it go, how do you calculate what goes which directions, and then we'll get into the specifics of runoff, which is one of those abstractions. We'll talk about hydrographs, which is essentially a time versus flow graph, and then methods of determining what runoff is, depending on what rainfall is in the situations that you're in. Then later, when we get into hydraulics of structures, we'll talk about the different kinds of flow, which will be pretty basic, pretty fundamental, but then we'll get into how you describe flow through a spillway, specifically if you're designing something that water's going to back up behind, such as a dam, or a culvert that maybe can't pass the entire flow that you're subjecting it to, so it builds up behind it, changes the flow characteristics. There's such a thing as a stage-discharge relationship that we'll talk about. And then when we get to open channel flow, we'll talk about different channel geometries, how to calculate flow using Manning's equation, and then we'll get into some rudimentary grass waterway design, so you've got that background as well. First thing I guess you need to understand is the material I'm covering is probably 3+ weeks in a 3-semester-hour class. So I'm going to compress 6 lectures and probably 3 labs into 90 minutes or up to 2 hours. So I'm going to have to just hit the highlights. I'll do some example problems so you get a feel for what you're up against. My advice to you is do some review if you're not familiar with it. Tab your references. That's something that saved me when I took it. How long ago did I take it? 16 years ago. And it does. When you're doing test management with open book, the worst thing you can have happen is to know you've seen that problem somewhere, but you can't find it, and you waste a lot of time looking for it. If you can put tabs on your references so that you can get right to the runoff, right to the precipitation, that will help you do things much more efficiently when you're facing time constraints that you will face when you're doing an exam like this. Okay, let's talk about the hydrologic cycle. Now, if you weren't in the first one I did a few weeks back, and I'm recognizing a lot of the names, so many of you were in that. The Fangmeyer reference is to one of the most recent versions of the Soil and Water Conservation Engineering text. It was originally put together by Glenn Schwab way back in the 50s, and has gone through, it's now in its 7th edition. The 6th and 7th edition are virtually identical. The publisher just changed, with the newest publisher being ASABE, because the bigger publishing houses decided there weren't enough of them being sold, so they weren't interested, in ASABE picked it up because it's the fundamental text for this particular area. So when you see Fangmeyer 2006, that is really the same thing as either the 6th or the 7th edition, and the preface to the 7th edition is dated 2013, so it's pretty new. Looking at my shelf, I've got essentially all 7 editions. And I'm just looking quick to make sure I'm not misspeaking. Actually, I'm misspeaking. The Fangmeyer et al. 2006 is actually the 5th edition. There has not been a lot of changes between the 5th, 6th, and 7th, but there are some. So whichever of those editions you have, it's one that's worthy of bringing along and knowing exactly where stuff is in it. Anyway, hydrologic cycle. Essentially what we're looking at is all the routes from clouds to ground to subsurface to lakes to streams back up into water vapor into the atmosphere again. And it's a cycle. And the main thing we do in hydrology is try to understand how frequently certain intensity of that cycle happens, the different portions of it, and how to calculate flow rates within those. So we'll talk about precipitation, how hard it will rain, how to measure the amount of precipitation that happens. When we get into overland flow, we'll talk about how to measure that. Infiltration, which is the movement through the surface, we'll talk about that. Pretty much the whole gamut of everything. We'll work through how to estimate what's going on based on the situation you're in, to get a feel for how that water is moving, because it impacts the movement of contaminants. It impacts whether or not you can grow crops. Just essentially everything that's going on is impacted by it. So we'll be using this concept throughout. When we get to the precipitation part of it, it's really the input to the rainfall runoff process. And you've got rainfall, you've got snow, which we've been having here in Champaign today, hail, sleet. You can measure it directly, but realize that it's going to vary both in time and in space. Sometimes very severely varying and rapidly varying in all dimensions. So you need to think through that as you think about how you're going to measure it. It's also affected by conditions that are going on while the rain or snow or hail or whatever is happening, and wind-driven versions of that precipitation can give you let's say difficult conditions to measure it accurately, and you need to take that into account. Rainfall data is out there. National Oceanic and Atmospheric Administration collects an immense amount of data, and it's tabulated on a daily basis, hourly basis, 15-minute basis, and then if the gauges that they're using are such that they can get a continuous report, those are out there. Now, usually those are more on the research kind of situation rather than maybe NOAA collecting it for everybody, but it's possible. The data is typically reported as a depth, but it's really a volume over a given area and then over a period of time, depending on what your needs are. If all you really need is daily moisture, daily rainfall, then the 24-hour rainfall volume is fine. But for other things, you might need it more detailed, and that data is out there. And then there's other ways to estimate it than just collecting it on the ground as well. So let's talk about average rainfall first, because if you think about it, if you've got a watershed and you want to size something at the watershed outlet that's going to have to handle whatever the rainfall is going to throw at it, you kind of need to know what an average is over a specific area. So let me show you an example of what I'm talking about. This first example is you've got a watershed. You're trying to do something with that outlet down there at the lower right, and you've got 6 rain gauges that are in and around the watershed itself. And for a given rainfall event, you've got the volumes as indicated nearest to the black dots. So those gauges, 1.9 through 2.2, if you just do an arithmetic average of those gauges, you get 2.0. Seems pretty simple. But if you look back at the distribution of these for a second, one would think that the rainfall on this watershed would be better represented maybe by the ones just on the watershed than the ones off. That's one way to argue it. You would get something higher than if you only included the ones inside the watershed. If you include all of these, you can get a different average. But let's say if there was one way down here in the lower left corner of the sharing window, would that be an appropriate gauge to use? And how do you judge what's appropriate and what isn't? You could have one 100 miles away. Is that appropriate? And those are the kind of questions you've got to kind of deal with. Well, they've developed a method for that, and it's called Theissen Polygons. The concept's pretty simple. If you're trying to determine an area or average rainfall for a watershed, you weight the influence of each of the rain gauges depending upon its portion of the watershed that it's closest to. That's the concept. So what they've developed is a method where you create polygons on that watershed where each rain gauge is the closest rain gauge to everywhere in that polygon compared to all the other rain gauges. I'll show you what I mean here in a second. I've done the construction of these Theissen polygons with that same image, and essentially it uses perpendicular bisectors. Now let me talk about that when I get you to the picture. Well, I've got it described, but when I get to the picture it'll make more sense. Essentially, it's a line. You draw a line between 2 points, and then you draw a line that is exactly equidistant between those 2 points, and along that line that joins the 2 points, and then you construct a 90-degree line to that point. That means everything on one side of the bisector is closer to its rain gauge than everything on the other side of the bisector is closer to its rain gauge. Let me show you what I mean. Here's the lines that I'm talking about. Let me grab my little arrow here. So for this rain gauge, when you draw a line between the middle rain gauge and the one to the east-northeast, I guess that would be north-northeast, whatever. The perpendicular bisector is this light blue line. And the way you construct it literally is to take a compass and scribe a line over here and then over here that is of one length, and then you take the compass to the other point and scribe and cross those points, and when you draw the line between them, that whole line is equidistant from the rain gauges. And I've done that construction then for every set of rain gauges. And the interesting thing, if you do it right by geometry, the perpendicular bisector between these two must hit the point that's the perpendicular bisector between these two and these two. It's just the way the geometry has to work out. So you should have these nice junctions at all points. If they don't come up that way, if you come up with one kind of in the middle here somewhere, you've done something wrong, because they've got to match that way. I did the proof one time just to satisfy myself that that is the case. So essentially what you end up with then is you've got these nice polygons, which I have colored a uniform color. The rain gauge that is within it is the closest rain gauge to that area. In the case of this 1.9 rain gauge that's up in the upper left, that's outside the watershed, this small light blue area is the area within the watershed for which that rain gauge that read 1.9 is the closest. Similarly, way over here on the one on the east, the 1.8, this kind of medium blue is the area that's closest to it rather than to one of the ones inside. So then you've got another concept that actually you're going to find we use a time or two more as we work through some of the hydrologic processes, is the area of areal weighting. In other words, weighting by relative areas of these portions of the watershed. So what we're going to do is take the rain gauge reading, multiply by its area of the watershed that is closest to it, sum all those products up and divide by the sum of the areas of the watershed, and you end up with an area-weighted average rainfall. Let's look at the actual calculation of that. So here's how you calculate it, and I just mentioned it. And this one hint in the middle here is important. A lot of times when you're dealing with this in a problem, you wouldn't have this on the exam because nobody's going to have planimeters with them, which is a mechanical device to measure areas. But if you're doing it in the office, you may use a planimeter to figure out what the areas are. When you do that, use the sum of the areas that you calculate, all the small areas, add them up and use that as the denominator, not the known watershed area, because if you made a mistake in your determination, you're going to compound it by using a known area instead of the sum of the areas. If you use the sum of the areas, you're going to still be very, very close to what the average Theissen rainfall should be. Now here's how we go about it then. And I'll kick back to the figure as I need to, but if you remember that 1.9 had a pretty small area, 65 was what the area reading was. The 2.1 in the middle, actually the 2.1 in the upper right, has a much bigger area, so you're multiplying by 150. The 2.2, which is actually wrapped around the corner here, has the biggest area at 270, and what you're doing then is you're weighting each of those rainfalls that those gauges are experiencing by their relative area on the watershed, and then you divide by the sum, and you end up with 2.07, which, since everything in here is two significant digits, you'd want to drop to 2.1, so the answer would be B of the choices that we gave you, and you've got your answer for the problem. Now, that's not all that different from 2, and in most situations it probably wouldn't matter whether you did the average arithmetically or this way. As the watersheds get bigger, it gets more important because you'll have more variation in the rainfall rate because of the way the big storms are, which are usually the ones of interest. The thunderstorms that typically we get in the Midwest in the summer have such varying rainfall that you could be really surprised by what the average comes out to be compared to just looking at the rain gauges and kind of averaging them. So this is one method of doing it. There's a couple of other ones. The nice thing about this one is, if you think about it, if the rain gauge network does not change, so for this watershed, all 6 of these rain gauges are always operational, and you've always got a volume for each rain event that you're interested in, the areas don't change. So your Theissen polygons don't change. Now, you could have a situation where maybe that one that's up in the upper left goes down, so you don't get data from it. Then you have to reconstruct the polygons, because all of a sudden, if this one, let me grab the little arrow that I keep forgetting to grab, if this upper left one, goes away all of a sudden, now this bisector isn't interrupted by this one because this one doesn't exist. So it goes straight out, and this one over here goes straight out, and all of a sudden this central area is bigger, and each of the two, the upper right and lower left, are both bigger as well. And you could work your way around and have the situation where any one of the gauges goes down, then you'd have an alternative set of polygons for that situation. Usually you're going to assume they're all up. You'll deal with it when you have to, but it's something to think about too. But the nice thing is, if they're all working, nothing changes. There's another method that I don't present in the review because it would be very difficult to put on an exam just because it's so time consuming, is a method called isohedral. And essentially then what you do is, with each of the rain gauges, you do literally a contour map in between the rain gauges, So you do a 2-inch contour that would come in somewhere, well, come in about midway here between the 2.1 and 1.9, and come down here somewhere because it's about a third of the way between the 1.9 and the 2.2, and then halfway between the 2.1 and come out. And you just essentially build those contour lines, measure the areas around them, and sum them up again. It's a bit more complicated because every time it rains, that method's going to change. So the Theissen is popular for the simple reason that once you construct it, if the rain gauges are all working, it's going to continue to give you the numbers, and it's pretty straightforward. So that's how you would do a Theissen calculation. And that I have not seen the exam. I can't help with the questions because I'm doing these review sessions. But if I was going to be putting in a hydrologic question, this is one of them that is pretty straightforward. If you provide the areas and provide the rainfalls, that you could have something that is easily answerable, assuming the student knows what they're doing. And if they don't know what they're doing, they're not probably going to be able to pull it off. Any questions on the Theissen polygons? Go ahead, Steve. Okay. The difference related to them is, let's say, here's the big watershed. And if you made a major mistake with the planimeter when you were measuring this middle one, and it's really 250 instead of 270, so you're talking almost a 10% error. If you then take your planimeter and trace the outside of this whole watershed and get the correct area for the whole watershed, now your weighting factors in the numerator are not the same as the sum of the weighting factors aren't the same as the denominator that you're using. So the recommendation is use whatever areas you get for each of these individual areas, sum them up and use them for the denominator rather than the known or measured area of the watershed, because you reduce the error. Okay. Anything else on Theissens? The concept of area weighted will come up again when we're dealing with some of the runoff calculations, because it's a nice concept to use when you've got some fairly simple aerial variation variation across a watershed that you know. Okay, let's talk about return period for a minute, because this is a really fundamental concept that you're going to need to understand to be able to interpret some of the problems on the exam. A 10-year, 24-hour rainfall volume is that depth of rainfall that lasts over a 24-hour period that is met or exceeded, and that's very important, met or exceeded on the long-term average once every 10 years. So the reason I emphasize that met or exceeded is understand that the 100-year event, which is a more extreme event, is included in the group that you'd be dealing with. So that would, the other 9 years would be something other, but that 1 year, the 100-year event, would take care of this 10-year event issue. That's more detailed than you need, just kind of confuses it. But realize that met or exceeded is important. Another way to describe it is the 24-hour rainfall depth that has at least a 10% chance to be met, or that has a 10% chance to be met or exceeded each year on the long-term average. Now let's look how that gets used. First of all, understand that it's been tabulated, and it was done quite a while ago. The reference that I usually talk about on this thing is HP40 or TP40, Technical Product 40. That was back in, or technical paper, excuse me, back in 1961. It's been updated. You can go on the web now and pull it up and get it electronically instead of by map. But back then it was literally a book with map after map after map after map. And this particular one is the 100-year 24-hour pattern in the United States. And you notice, I should just leave this arrow out here. It's kind of nice and uniform, pretty simple in the eastern part of the U.S. unless you're in some of the more mountainous parts of the Appalachians. But boy, when you get out west, it gets really crazy in spots. And in fact, there's a map for Hawaii and Alaska too. And you can imagine when you get around the mountains, it does change an immense amount. So it's something that if you're going to work in that area, you want a more detailed map. What NRCS has done is they have it tabulated by county. And if you go into their field office tech guide, there should be a map somewhere. Excuse me a second. A map or a table that will give you various years, various durations for every county in the state that you're dealing with. I know in Illinois it's like 4 pages and it goes from 1 year to 2 year to 5, 10, 25, 50, and 100 year. And you can get it, and that's just the 24-hour, but you can get it for lower durations as well, and actually longer durations too. Now, what they've done, and we've done this for some smaller watersheds around Champaign-Urbana, it comes from historical weather data, and essentially you do analysis based on the data that's available and run the statistics, and then you can put it together for a specific location. As I mentioned, it's in tabular form on the website or in state reports, and then national maps from various references, which is probably the way you're going to have to access it when you're taking the exam, is you're going to need to be familiar with the maps and be able to read off those maps. So that's why I've got an example in here to take a look at that. So you're going to be designing a reservoir. It's going to be designed to contain the runoff from a 10-year 24-hour event in northeastern Illinois. What rainfall volume is to be considered? So 10-year 24-hour rainfall event. That means you've got to go to a map, and here's your choices: 4.5, 3.9, 4.1. You can't estimate it. Northeastern Illinois, on that style map, this particular one is the 10-year 24-hour map. It came from the Hahn, Barfield, and Hayes book, but there's a similar map in all the Schwab books, so it's available. And essentially, you go up in this area. That's northeastern Illinois, right there against the lake, mostly Chicago and Lake County north of it. And then you're looking at this line. Kind of goes right across the tip of the lake, and it's not totally obvious from this scale, but this number right here is a 4. You see 3.5 there, and you've got 5 here, and you can see the 4 better down here, and you just kind of follow it along, and there it is. Now, northeastern Illinois is kind of a little bit this way from just that line. So you know, of the choices you've got 3.9, you've got 4.1, you've got 4.5. Now, you've done it. Everybody on the call here has done enough topographic maps to know that if 4 is here and 5 is here, 4.5 is out here in the middle somewhere, running about through Bloomington normal. 3.9 is going to be between the 4 and the 3.5, which means it's out here in the lake somewhere, which means 4.1 is the right number. And from looking at this, you can estimate it from the map. So 4.1 is the correct answer. And that's the one you would use. So that's pretty straightforward. And that's really as hard as some of the questions may be on the precipitation. But if you think about it, you've got to know where to look. Now, that's just precipitation, just return interval, and picking a design depth. We'll get into some more stuff here in a minute. But Any questions at this point on what you've seen so far? Okay, I'm trying to make sure I go fast enough, but not too fast. Let's talk about abstractions from rainfall for a minute. Essentially, the abstractions are the losses that do not show up as runoff. Okay? They are things like interception. Interception is that part of the rainfall that ends up being retained on leaves, on trunks, tree trunks, etc., so that it's intercepted before it hits the ground so it can't become runoff. It may later become part of this evapotranspiration, which is a combination of evaporation and transpiration. It goes into the plant. It may be taken up from the ground. It evaporates from a water surface, does something other than runs across the ground. It could be in storage, could be sitting on a surface like on a parking lot that's flat enough that water stays on it until it evaporates. It could be in a bank. It could be on a plowed surface where it's sitting there in depressions until it either soaks in or evaporates. And then there's infiltration, which is the movement of water from the surface of the soil through that soil-air interface into the soil itself. So it's going into the pores of the soil. When you add all those up and subtract them from rainfall, what's left is runoff. Runoff is called a few other things. I've seen it called effective rainfall. I've seen it called rainfall excess. Pretty much runoff is the word that's used most of the time, but just in case. So let me give you a text description and just kind of imagine this as I walk you through it. If it's raining faster than the soil can take it in, you're going to start getting some ponding. Water's going to accumulate on the surface. If there's any roughness on that surface, that means there's going to be water stored on that surface because it can't flow freely away. It's going to sit there in a depression of some kind. But after some of those depressions get filled with water, you're going to have some water moving down slope. And as more rainfall continues and as it fills more of that depressional storage, the runoff rate's going to increase as more of the hill slope contributes. So as more of the depressions on the surface fill up and they overtop and start flowing downstream or down gradient, eventually you're going to start getting measurable and perceptible runoff that will flow into a major channel and then end up leaving the watershed. And that's essentially the runoff process. If you don't have a rainfall rate that's high enough to exceed the ability of the soil to soak it in, then you won't get runoff. You've got to have ponding start first. If there's virtually no storage on the surface, you'll get runoff immediately. If there's a lot of storage on the surface, such as into a plowed field or something like that, where you've got a lot of roughness, you may never get any runoff because the rainfall doesn't fill the surface ponding capacity. So there's a lot of trade-offs that each situation is a little bit different. And that's why when we start talking about runoff, the surface conditions play a major part in how much you get and when you get it. So here's the process. And let's see if my little animation works here. Yeah, okay. Let me back up and talk about it for a minute. Rainfall runoff process. You've got a nice uniform rainfall. Idealistic, I know. Hardly ever happens in the real world, but to get you the concept, we're going to set it as a constant. You've got a runoff capacity. I'll be that way. There we go. That the soil can take in water, and as it takes more water in, it can take less in on a rate basis. So the rate curve for runoff capacity is that sloping curve there. And then let's see what it does from there as far as runoff. So what essentially the amount of infiltration is equal to the rainfall rate, while the ability to take water in, the infiltration rate, is above the rainfall rate. So it's nice and flat right along the rainfall for a while. And then it follows the infiltration curve, whatever that function is. In this case, they're using a nice decreasing curve, which is typical of what it looks like if you've got a uniform rainfall. Runoff, then, is the difference between the two. So while it's up here, you've got no runoff. When rainfall starts exceeding infiltration, or conversely, infiltration rate starts getting less than the uniform runoff, then, or uniform rainfall, excuse me, then the difference between them is the runoff. And actually they cross, and then you've got runoff as infiltration goes toward a constant, conceptually the saturated conductivity of the soil we're talking about. Runoff is going to go to a constant rate as well. Real idealistic, but that gives you the concept of what's going on when you've got rainfall on a soil that just continues, and how the runoff and infiltration interact. So the runoff is the blue curve when you get all done. Okay, now another concept. This is when we start getting into watershed flow. The time from the beginning of runoff anywhere on the watershed to the time at which the entire watershed is contributing runoff that reaches the outlet is called the time of concentration. Now, the concept here is important. You can have runoff happening locally everywhere on the watershed all at once, but you won't have it contributing to the flow at the outlet until you've had enough time pass to cover that travel time from the hydraulically most remote point to the watershed. That's why it's described that way. At that point in time, the entire watershed is contributing to the flow at the outlet, and you've taken care of the time delay that you would have physically, because water doesn't flow instantaneous to the outlet. It's going to take some time to get there, and the amount of time it takes to get the entire watershed contributing is a concept called time of concentration, T sub C. Now, let me talk through the curve number method with you. And when you see this, it'll frequently be referenced as the SCS curve number method. And it depends on how old you are, whether or not you even know that the USDA agency currently known as the Natural Resources Conservation Service was actually the Soil Conservation Service quite a while ago. I don't even remember when the exact date was when that name switch was, but it was reasonably early in my career, and I started in 1985 at the University of Illinois. So it was 90-ish when they made that change. This was developed quite a bit before that, so it's just, to a lot of us, it's just the SCS curve number method. Essentially, the concept was that somehow we have to come up with a way to predict what runoff's going to be based on rainfall and based on the conditions of the soil that you're dealing with. So it uses first the idea of an initial abstraction. Essentially, all the losses, all of the rainfall that happens before runoff begins is the initial abstraction, and then you've got more abstractions from there. But that's the water that's initially not part of the runoff process. And they put this together and then fitted it to studies that they had worked on, that they had data from, and came up with a nice method. Now, the equation is something that you could use. To be honest, it is seldom used. You have to recognize that there are assumptions like this initial abstraction being equal to 2/10 of the maximum retention. It's something that they've figured out based on studies, and it's a fitted parameter, but it works. So understand where it comes from, but more likely you'll be reading it off a chart. So essentially what they do to get to the curve number is they take the equation and do some solving to end up with a function of P, the precip, Q, the runoff, and I hate the fact that they used Q for this because Q is typically flow rate in cubic feet per second, but in this case it's runoff in inches or centimeters. I wish they hadn't done it, but they did it and it's stuck, so that's the way it is. They define curve number as a parameter that takes into account this initial abstraction parameter, the maximum retention storage. And if you look at this parameter of curve number, as the retention storage goes to 0, this S, curve number goes to 100. So if a surface is perfectly impervious and such that there would be no roughness, so there's no storage on it, then you'd have a curve number of 100. Anything else is going to be a curve number less than 100, and it depends on how big this gets. Okay. Now, time of concentration is also a nice fitted equation if you need it as such, as a function of curve number. Now, when you see an equation like this, you always have to wonder, what are the units and how did I get it? Well, curve number in this particular one is in hours. Okay? Flow length is in feet. Curve number is dimensionless. Y is the slope in percent. When you've got an equation, you've got to make sure everything's in the right units. Okay? If you put watershed slope in feet per feet, like you would tend to do in Manning's equation that we'll see later on, you get garbage as the answer. If you put flow length in meters or miles, it's going to mess things up. Or if you assume the time of concentration is in minutes instead of hours, etc. You can tell it's a regression equation because you've got units here, feet to the 0.8. This is a dimensionless, and yet it's to the 0.7. And then you've got down here percent, the square root of percent. I mean, this is something that doesn't have a physical reality, but it is a useful equation, and I've used it in design situations, and it's okay. It's better than having to try to estimate it some other way. So you've got at least an idea what's going on with the time of concentration. Okay, let's talk about curve number for a minute. SCS and NRCS and ARS, essentially the research agencies of USDA and the universities, have done a lot of work with the curve number through all the years. And there's tabular values for all kinds of different soil surface conditions. You also have the concept of hydrologic soil group that comes into this. Now, if you think in terms of soil textures, you're going to have sandier soils, pure sands down in the A's. You're going to have much less permeable soils such as silty clay loams, clays, those sorts of things in the D, and then you've got ones in between. You can't make the direct assumption, though. You need to go look things up, because I was working on a project at Fort Bragg, North Carolina, and the soils that I was looking at were really sandy, And I was thinking, okay, that's probably an A, maybe a B. No, they were C soils because they had clay lenses that stopped things from soaking in. So even though the surface is sandy, the subsurface was changing what the actual hydrologic soil group was for that particular soil series. So you can maybe do an estimate based on the texture, but you really have to look at the detail if you're gonna do the end calculations. Um, and these are all tabulated somewhere for the soils you're dealing with. If you've got fallow soil conditions, so it's just bare, you're going to use these top numbers. If crop residue has been left but it's in poor condition, you're going to use the second ones. If the field has not been compacted, it's got pretty good residue cover, but it's not growing a crop, you'd probably use the bottom numbers. If it's row crops, you've got a full set of conditions that you can work with, and then you can calculate runoffs from them. Now, the other thing, there's many, many more. This is just an example. There's many, many more pages of these curve numbers, including disturbed areas and subdivisions and developed urban areas. And you'll see some of those here in a bit because we'll use them for an example. But this is an example of the kinds of information you'd have to have. Okay, so how would you determine it? Well, these curves, this chart, is based on the equation that I showed you before. And essentially what you've got then is you enter it with a rainfall. You know your curve number because you know the watershed you're dealing with, soils and soil conditions. So you can read, let's say you've got a rainfall of 7 and you come up and you've got a 50. You just take the 7 line up to 50 and read right over and you get something right around maybe 2.1. As an example. Now I do have an example here in a minute. We'll run through it again. But these charts are available, and this is in, I think this came from the Schwab book. If it didn't, it came from something similar to it. So it should be in virtually every reference for soil and water engineering that you bring along. So let's do an example. Previous problem, we figured out the design rainfall in Northeast Illinois was 4.1 inches. That's a 10-year, 24-hour event. Assuming the watershed in question is a completed 300-acre residential area with an average lot size of half acre, all on hydrologic group C soils, what's the needed pond volume if all runoff is to be retained? Now, realize that this is a specialized question because you would very seldom try to retain all the runoff. You'd have some kind of spillway. But so that you don't have to do a spillway routing, let's define it as all runoff to be retained. What's the volume you'd need? Okay, you've got several different units, several different values. Let's take a look at what you got to do to make it, to figure it out. Okay, here's another one of those charts that I was talking about. You've got urban districts, commercial business, industrial, and then different residential areas by average lot size. And essentially what you're doing is setting the percent impervious. And impervious areas are by definition not 100 because they usually have a roughness, so they retain some rainfall. But they're usually just defined as 98 as a curve number. So let's see what we got to do. We had C hydrologic group, and if I remember right, we said quarter-acre lots. No, half-acre lots was what I specified. Let me back up, make sure. Yep, half-acre lots. Okay, so that means we've got a curve number of 80. So we've got 300 acres with a curve number of 80. What's the volume of rainfall we're going to deal with a 4.1 inch rainfall? Okay, so here's the chart. We'll take 4.1 and run right up vertically to that 80 line. And I'll tell you from experience that this chart with these curves, if you don't have a number that's right on 80 or 85 and you've got to interpolate, it gets, you you've got error you could introduce, let's put it that way. So look really carefully, and sometimes, especially if they're not every one of them labeled, it's easy to get confused on the curve number lines too. So work through it carefully if you're going to do one of these. But 4.1, you're up to the 80 line, straight over to the runoff, and it looks like about 2.1 inches of runoff. Okay, so the answer in this case then is 53 acres, and where it comes from is you just figured out you've got a runoff depth of 2.1 inches. The full volume is then 300 acres times 2.1 inches. That's 630 acre inches divided by 12 is 53 acre feet. And that's where you've got to pay attention to the units. And if you were off by a tenth or you weren't paying attention, you know, one of the answers was 630 acre feet. You could have grabbed it, but that was not what it was. 53 acre inches, if you forgot the units, 53 acre feet, you know, the folks that are doing these answers can sometimes be a little tricky with giving you the options because they're trying to make you pay attention and seeing if you are. So 53 acre feet is the answer on that particular one. Let's do an additional one so that you see how you might use that same concept of area weighting that we used with the Theissen polygons. So after you've done the initial investigation, you discover the subdivision's actually 100 acres of half-acre lots on C soils and 100 acres of half-acre lots on D soils, 50 acres of quarter-acre lots on B soils, and 50 acres of townhouses on A soils. Then what curve number would you use? Okay, here's the chart again. So you've got the half acre on C. Okay, we had that already. That's an 80. You've also got, though, half acre on D, which is 85. You've got quarter acre on B, which is a 75, and you've got eighth of an acre or less on A, which is a 77. What would you do with that? Well, same concept, area weighting. Correct answer is still 80, but for a different reason. You've got then the 80 curve number times 100 acres, the 85 curve number times 100 acres, the 75 curve number times 50, and the 77 curve number times 50, divided by the sum of 100 plus 100 plus 50 plus 50, which is 300, and that's 80.33, which, given the chart and how well you can do it, you're still going to call it 80, but it's a more refined answer because you've actually done that. And if, you know, for example, you had 150 acres on that 75 curve number, it would make a much bigger difference and you'd have something different, something below 80. So that's how you'd calculate it if you've got different land uses and different soils. You just figure out the combinations and sum them up and do the calculation based on the areas. Okay. Excuse me. The curve number method also has an opportunity to calculate a peak discharge. And by that, when you're dealing with a runoff event, it's not going to be continuous. It's not going to be forever. It's going to come back down again. And at some point, you're going to have a peak. You need to know the average watershed slope, the watershed flow path length, the average curve number, and a rainfall depth. And from the engineering field manual, here's what you've got as a chart. And this is duplicated in the references as well, typically. But you've got a time of concentration on the x-axis. You've got a unit peak discharge. Pay attention to the units now. You've got CFS per acre per inch of rainfall. Excuse me, per inch of runoff. No, it's rainfall. And then this parameter that you have to calculate. Let's look at this calculation for a second. We'll use the same residential watershed, produce 2.1 inches of runoff from a 4.1 watershed. Flow length is about a half a mile. Slope is 2%. Curve number is 80. So S, if you remember that from the curve number calculation, that's 2.5. Initial abstraction is 2/10 of that, so it's half an inch. Initial abstraction divided by P is half divided by 4.1, so it's 0.122. And that's what this parameter is that is kind of hard to read in the center, is initial abstraction divided by the precipitation. Okay. You could calculate a time of concentration. You've got the 2,500 feet. Raise that to the 0.8. This is that equation that you saw. 1,000 divided by the curve number, minus 9. Raise that to the 0.7, and then divide the whole load by 1,140, and by the slope in percent raised to the 0.5. You end up with a 0.8 hour after that calculation. And then you use the chart. You come up with 0.8. Now you'll have to watch both of these two axes, because notice you've got log scale on this one. You've also got a log scale on this one. So things are not uniform. It makes interpolation a little bit trickier. But we're heading toward 0.122, which I interpreted to be out in here somewhere. And then over. And you end up with a 0.5, probably 0.56, something like that. Let's see what I decided it was at the time. 0.57. Because remember, on a log scale, half is a little bit shy of equidistant. So interpret accordingly when you're dealing with a log scale. But this one I took as 0.57. It's CFS per acre per inch of runoff. So the peak discharge is calculated as 0.57 times 300 acres times 2.1 inches of runoff, and so it's about 360 CFS. Now, there's another method that gets used a lot, especially in civil engineering firms. It's called the rational method. Much more general than the curve number. C is a coefficient that you look up based on the watershed you're dealing with. It's about 0.4 in this case. We said A was 300 acres. I, which is the rainfall intensity of the duration, time of concentration. So when you look at the rainfall pattern, it's 2 inches in 30 minutes, 4 inches an hour. Peak rate then is 0.4 times 300 times 4 inches per hour, and you end up with a flow rate in this case of 480 CFS, which is 33% higher than this one. And it tends to give, rational tends to give larger flows, so it's more conservative on the size of the structure that you're going to put in, which is probably why it gets used. It's not the method I prefer, but sometimes you just have to, so you should be familiar with it and know where it is in the book that you're dealing with as your reference, so that you can look it up and do a problem with it if you're called upon to. Okay, questions on runoff? Okay. Let's talk about hydraulics of structures for a little while then. The flow-through structure is important because the structures themselves control the rate, and sizing of them gets important because you want flow to pass, but you've also got to be protecting downstream areas from the effects of too high a flow rate. They can also be used as a measurement tool. So depends on the structure you're dealing with, what kind of flow will pass by it, and the flow rate that is resultant from it. And we'll talk about several different kinds of hydraulic structures um, so that you get a feel for what's possible and what to expect. Weirs are the first thing we need to talk about. There's two kinds. And they're not all perfectly sharp-crested or perfectly broad-crested, but they would fall into these two categories because the equations are different. The Weir equation is pretty much the same. It's going to be some kind of coefficient times the length of the weir times the head, which is the amount of water before it starts flowing through the depth of water above the weir before it starts to be a curved surface as it flows through the weir itself. So it's a distance upstream, and you measure the height of water above the weir elevation. I'll show you a diagram here in a second. So if we're talking about a sharp-crested weir, with this being the sharp point, you've got to be at least 4 depths of water upstream to have a flat surface to measure, okay? And then as you get to the weir itself and the water's coming over it, then you start getting some strongly curvilinear flow, and it comes into the channel downstream of the weir and then flows off. This particular one is called a vented weir because you've got water air underneath that water flow so that it's fully vented. There's other ones that won't be, and you'll see those here in a bit too. So this is an open channel weir, sharp-crested. It's a nice weir for measuring water flow off of because the equation is pretty standard and well-behaved. Now, if it's just a straight weir across, sharp-crested weir here, just straight across, you've got the ventilation like I talked about, which means you don't have a backwater effect where this water downstream is actually almost as deep as the water upstream. But that's the equation you've got. The L is the length of the weir, which is the width of it away from us. And then you've got the ratio of the height to the head to essentially the height of the weir comes into play with these as well. If you've got a V-notch weir, in this case, you've got the flow rate through it, and Q in this case is flow rate in volume per second, or volume per time. You've got a coefficient, trigonometric function, tangent, and then you've got the angle divided by 2 times the depth. So you've got the tangent of the half angle times the depth raised to the 2.5, with K being somewhere between 2.5 and 2.7. If the angle is 45 degrees, Q's 2.5. Excuse me. If the angle is greater than 45 degrees is what we're talking about for here. If it's 90 degrees exactly, then Q is 2.5 times H to the 2.5. Broad-crested weir has a similar function, with L being the width of the broad crest. Side contracted weir, by this we mean the flow upstream is all the way out to the far edges. The weir itself is narrower, so that you've got flow that will kind of pile up and has to go through it. That has a different equation as well. And this is all from Hahn, Barfield, and Warner. Okay, let's look at some of these. Here's an example. You're going to measure flow. You've got a 90-degree V-notch, which is a typical one you'd use for flow. H is measured as a little over half a foot, at 2.5 feet upstream from the weir, what is the flow rate? Okay, and you've got the choices of 230 gallons per minute, 0.51 CFS, 0.51 gallons per minute, and A and B, indicating that those are the same number. And that the answer is actually A and B. Okay, the equation, which I just gave to you, is 2.5 times h to the 2.5, because we have a 90 degree. And when we do the calculation, then we've got 2.5 times h raised to the 2.5. Q is in CFS, h is in feet. So 2.5 times 0.53 feet raised to the 2.5 comes up to 0.511 CFS, or 0.51 CFS to 2 significant digits. But if you do the conversion by multiplying by 60 seconds per minute and then by 7.48 gallons per cubic foot, you figure out that it's also 230 gallons per minute. And note that both of these two contain 2 significant digits. Okay, another kind of flow is orifice flow. And there's differences between a submerged orifice and a free outlet orifice, with a coefficient involved in the equation, then the shapes of the orifice affects that. So here's a submerged, where you've got a water tank of some kind, you've got a hole in a wall of it, you've got water on the outside, and what you've got is flow coming out here, but because it has to contract, it's got this nice sharp edge as well. You end up with some swirls, and you've got less head here than here, and that's what's driving it. But here's what the equation looks like then, is you've got 2 different coefficients that get put together to be a coefficient. You've got the area of the orifice, and then you've got gravitational and the difference between gravitational acceleration and the difference between the heads. And that's essentially, area times velocity is flow rate. So that's what you're trying to calculate here eventually. Free discharge orifice is one that is going from a tank into the atmosphere. So you've got atmospheric pressure out here. You don't have a hydrostatic pressure on it, which is what the difference in heights is essentially calculating. So in this case, it's just 2GH rather than 2G times the difference in heads. And again, you've got a coefficient in the area. So similar. Things vary depending upon how nicely shaped things are. If you've got a sharp opening, it's going to be different than if you have a smoothly rounded opening. And that's going to be different than if you have a tube. And that's going to be really different than if you have a protrusion into the deeper water tank that then it's coming out from there. And of course, we were talking about the 2 different coefficients, and those come into play. But it's usually only one that you use, and you can see if you've got a nice smoothly rounded, you're going to have a very high coefficient compared to the protrusion into the tank, which is about half as much flow. Okay, so let me give you an example of that particular one. Now, I did some graduate work at Kentucky, and we discovered Maker's Mark, so I decided to use it as an example. They just moved a 3-foot diameter barrel into the bottling plant, and they're going to empty it into their charcoal filter. By the way, we've been there when they've done it. They removed the plug, and it was removed instantaneously. Remember, this is an example, so we've got to make it simple. So it's flowing freely from a 2-inch diameter hole. That can be considered a sharp-edged orifice because this is a oak barrel, so it would have fairly nice sharp edges. What's the initial flow rate, assuming the specific gravity, same specific gravity as water, which is also an incorrect assumption, but it makes it simpler to deal with. Here's the answers. Half a CFS, 83 gallons per minute, 26.6 gallons per minute, and 200 liters per hour. So what is it? How would we go about it? Well, it's an orifice flow equation. Said it was a sharp one, so 6.61 is the typical coefficient. You go back and look at it and use it up. You got an area. You got 2g raised to a square root times the head raised to the square root, because you can separate those out. The area is pi times the radius squared. You've got 32.3 feet per second squared is the gravitational acceleration. Okay, you see where it's all coming from. Then you just do the math and you end up with 0.185 CFS. Do the conversion, multiply by 60, multiply by 7.48, and you end up with a Q of 83 gallons per minute is the initial instantaneous flow rate. Now, of course, as the head drops, it's going to slow. So that's why it was specifically asked to be the initial flow rate. And that's how you go about calculating with the orifice flow equation. When we get to pipe flow, it gets even a bit more complicated. Now, if you were on the earlier webinar I did on some of the fundamentals, we talked about Bernoulli's equation, which is an energy balance equation. And essentially, you're looking at any two arbitrary points on the streamline. The energy is a constant if you take everything into account. You're going to have some frictional losses. You're going to have input to the equation or input to the energy if it's coming from a pump or something like that. But it's got to come out as balance. So we can use that to our advantage as well. But that's basically the equation where you've got pressure at the two different locations, you've got height at the two different locations, and you've got the velocity head at the two different locations, and they have to be a constant and have to take into account the losses. Okay, and the losses during pipe flow are pretty well documented, and they can be extreme. You've got an entrance loss. Essentially, you've got flow going into a pipe. If you think of it as the protrusion in the orifice, that was a pretty hefty change in coefficient. You've got a bend loss, so if you've got a change in direction of the flow because it's got to come from a vertical pipe into a more horizontal pipe, you can have that. All the way along a pipe, you're going to have friction losses, and the references are there. So if you or the coefficients are all documented in the various references. So if you look at the Bernoulli equation for a spillway, you've got pressure is the same at the reservoir and at the exit, so you don't have to worry about that. Elevation different is the water surface elevation difference between the two, and the remaining is velocity head and losses, so you can add them up. But let's look at what this thing would look like. Let's say you've got a spillway that looks like this. You've got a height of water over it, and then you've got this height and length of this spillway. And you can look at, and this is a classic picture out of a fluids book that you'd use in a civil engineering class, typically. That's where I remember it from. And so you can get them all added up. You've got a head on the pipe, you've got a loss, you've got a velocity head, and all of the losses are proportional to the velocity head. In this case, you've got the one in here takes into account the exit loss. You've got an entrance loss. You've got a barrel, or excuse me, a bend head, and then you've got a friction that's a function of the length that you're dealing with, including the riser. And you come up with a discharge based on all of those losses and the velocities that you're dealing with. What I'd recommend you do if you have to do this kind of a question is to find an example and have a pipe flow example marked as a tab, and then you can just kind of work your way through it. Okay, what about spillways? First of all, you've got to understand that they may have several discharge relationships depending upon what the depth of water upstream of the spillway is. And I'll give you an example of it here in a minute. The stage discharge curve then becomes a combination curve. I mean, you're going to have one part of the curve that's a weir, one part of the curve that's an orifice, one part of the curve that's a pipe flow, depending upon what's going on with the spillway and the given storm or flow-through event that you're dealing with. So let me give you a picture here of what we're talking about. Here's a barrel riser and pipe spillway for a dam, and under the various different potentials you're going to have. In the case of A, you've got orifice flow. There's not continuous water through here. Essentially, the control surface is the edge of the pipe, and then whatever depth it fills up to, you're still going to have air throughout, and it's really the weir equation that's going to dictate flow through it. When you get to B, you've got a totally submerged entrance, but you've still got air in the system. And essentially, this is going to be dictated by the orifice equation, because it's going to act like an orifice with the air, going into an atmospheric area, kind of like a reservoir. This is turned sideways compared to what you saw before, but you've still got a jet here, if you want to think of it that way, surrounded by atmospheric pressure going into a pipe and on its way out. When we get down to C, we've got a situation where you've got full pipe flow, but it's going into atmospheric conditions. So you're eliminating the velocity head as it falls out of the far end. And then in D, you've got backwater conditions on the downstream pipe. So that the important head is the difference between the two rather than essentially the head above the outfall. And that's the four conditions we would deal with. Okay, so what's a stage discharge curve then? Well, we've got the weir equation, which is this really steep one here. You've got an orifice equation, which is along here. And you've got the pipe flow that's here. So what we end up with is a situation where you've got a composite curve where, with heads up to some small amount here above the inlet, where it's a weir, you follow the weir equation. From that point out to when it goes to full pipe flow, somewhere out about, in this case, about 7.5 feet, you follow the orifice equation. And from then on, it's full pipe, and you follow that one. Now, if we had a situation where it went to a backwater in addition, you could have a fourth curve as that backwater kind of filled up. And the way you know where the transition is when it crosses the next one. It always starts as weir, as water comes up slowly above the outlet. It's going to start as weir because it's just kind of cascading over it. When it hits the orifice equation, it's going to take off on it. And then when it hits the pipe flow equation, it takes off on that one. Because you can, in those cases, you can move a lot more water more efficiently with those. It's just the flow conditions transition in that order. Okay, so here's an example. You've got a 18-inch corrugated metal pipe with an 18-inch vertical riser. It's used as the principal spillway for the pond. The pipe is 50 foot long with one 90-degree bend. The top of the inlet is 10 feet above the bottom of the outlet. Develop a stage discharge relationship assuming a free outfall. So you grab the equations you need, the basic weir flow equation with an 18-inch diameter riser. The length of the weir is 2 pi r, or about 4.7 feet, so you can pop that one in there. So you got 14.7 times h to the 3 halves. The 4.7 times the 3 is where the 14.1 comes from. So that's the equation for the weir. On the orifice, you've got a coefficient. You just have to assume a C. It's usually, with a situation like this, 0.6 is a pretty good assumption. You've got an 18-inch riser, so you've got A is that of an 18-inch, so you've got 1.5 is the diameter, so you can do pi d squared over 4. You end up, when you do all the calculations, you end up with 8.51 times h to the 1/2. And then the pipe flow, you look up each of the parameters based in the example you found in the reference, and you can figure out that you end up with another equation, which is 5.8 times h plus 9.1. And if you remember back when we looked at the chart, the pipe equation didn't start at the origin, the other two did. So in this case, you've got one that's offset by 9.1, and then it's the square root of that. So when you put them together, you end up with this. Back up. So you end up with the weir equation, the orifice equation, and then the pipe flow equation. And the pipe flow equation comes out, hits the axis appropriately for 5.8 times h plus 9 square root. That's how you do it. You'd end up with 3 different equations, and they just transition from one to the other as the water got deeper in the reservoir. Questions? It's all a matter about identifying the spillway you're dealing with, finding the right equation for it, and, reducing from the description of that weir or orifice or pipe flow to what the actual equation of the flow is, and based as a function of height, and then putting them on a chart. Okay. One more section, and that's on open channel flow. And it's an important area. Probably would have been a civil engineering class. We'll talk about grass waterway within this one too. Probably a couple of different classes that you had which would have dealt with this, but flow through open channels is important, and usually Manning's equation is the one you use. There's some other ones you could use, but this is the basic one that most everybody uses, so we'll stick with that one. Here's the equation. You've got velocity in feet per second. You've got a coefficient Manning's n. You've got a hydraulic radius, which I'll define, but it's in feet. You raise it to a 2/3. And you've got a energy grade line, which, if it's normal flow, is the same as the bed slope. It's in feet per feet. Okay? Now, you heard me say English units throughout. If you're dealing with metric, SI units, flow in meters per second, there's no 1.49 because that's the unit conversion. Hydraulic radius would be in meters. Slope would be in meters per meter, which is the same. Okay, let's see how this thing would work. It's going to depend on the channel geometry, because hydraulic radius is defined as the area of the flow, whatever that is, divided by the wetted perimeter of the flow, which for open channel flow is from this edge along the channel all the way up. So area divided by wetted perimeter. So if you've got a nice shape that has no fixed bottom like the trapezoidal does, you end up with a hydraulic radius that is a straight function of depth. If you end up, excuse me, if you've got something that's got this fixed width here, then all of a sudden perimeter isn't a straight function of depth. It's a function of depth plus this width. So, and an area is too, so it gets a little more complicated. But you can calculate the top width. You can calculate the top width with freeboard. It just depends on how you need to use the dimensions of your channel. But let's look at how things get used. Here's the Manning's End values. They're tabulated. It's essential. The concept is it's a roughness as experienced by the flow. So these are fairly smooth. The smaller the Manning's End, the smoother the surface. So think about it. Corrugated metal is going to have a higher Manning's End than smooth metal. Concrete that's kind of a rubble concrete is going to have more roughness than finished concrete. Planed wood is going to have a smoother surface than unplaned. So, I mean, that's kind of the way it works. So let's do an example. Flow rate of a regular finished clean concrete channel, base width of 8 feet, channel slope of 0.5%, with a normal water depth of 2 feet. What's the flow rate going through there? Could be 140 CFS, 8.5 CFS, 100 CFS, or 200 CFS. Here's the solution. Velocity, 1.49 divided by n. Hydraulic radius raised to the 2/3, slope raised to the 1/2. So n for that particular surface is 0.015. Hydraulic radius for a trapezoidal channel is going to be 8 times 2 square feet. Where'd the 8 come from? Where'd the 2 come from? Well, let's back up and look at that equation for a second. We said it's a base width of 8 and a normal depth of 2. So the area is going to be the base times the depth plus the side slope times the depth squared. And the equation for the wetted perimeter is kind of a messy one. It's a geometric equation. But let's go ahead and look at it here. So that's where this comes from. You're adding depth the base times the depth, and then you've got, and you're dividing by the wetted perimeter. So you end up with calculation there. You've got 0.005 feet per feet because it was 0.5%. Velocity when you calculate it is 8.5 feet per second. Multiply, because you figured out the area was 8.2. Okay, that's where I just messed everybody up. Rectangular finished clean concrete channel. Rectangular. So I went to the trapezoidal, which it messed you up. The area of a rectangular channel is the width times the depth. The wetted perimeter is the depth on the left side plus the width plus the depth on the right side. That's where it came from. We got the slope 8.5 feet per second when you do the calculation. The area then is just that nice 16 square feet, the width times the depth times that velocity. You've got 140 CFS. So the answer is A. Sorry about that little mess up. Okay, vegetated waterway design. This is the last part of this particular presentation. It's an iterative process. Think about a vegetated waterway for a second. Essentially, it's a open channel which has a change of roughness depending upon whether the grass is unmowed or mowed. If it's unmowed, it's going to be resistant to the flow. You're going to lose capacity. You're going to have slower flow through it because you've got this grass that's just going to slow things down. If it's recently mowed, you're going to have higher velocities, but you could have the problem of erosion bed scour because you've got high velocities. Now, the engineering field manual has tables of suitable dimensions that they've pre-calculated, which is the method that gets used for vegetative waterway design. It used to be that you'd have to go in and do a full iterative process, first looking at stability and then capacity and making sure that you matched everything up for both mode and unmowed conditions. Now they've got it set up so that you actually walk through steps, and what I'd recommend you do is find this design steps, and this is in many of the references as well, or if you've got a bound copy of the engineering field handbook, you can use it. But you figure out what you've got to deal with. So you've got a peak runoff that you've got to determine. So let's just go step by step. It's probably the easiest. You have to look at grade changes. By the way, this comes straight out of the engineering field manual, but you have to figure out the watershed area for the points that you set and for the outlet. Determine the peak runoff, the slope of the channel that's going to be out there, approximate channel cross section. Usually you usually go for a parabolic channel because the contractors can put a straight segmented channel out there with the equipment that they use that as flow goes through it, it naturally goes to a parabolic channel. You look at the soils you're dealing with and the grass that you're going to plant so that you can get the maximum permissible velocity, which would be when the grass is mowed. You check the channel for adequate capacity using Manning's equation at the flow rates that you're going to be dealing with and the velocities that you can tolerate, and then you select the waterway depth from the charts that you have available. So let's do an example, and then we'll go right into the charts, and you'll see what I mean. You've got a subdivision that's got a peak runoff rate of 60 CFS from a 10-year 24-hour rainfall. You've got a vegetated waterway that's going to be the outlet of this thing. Average slope of 3% is going to have Kentucky bluegrass in it. The soil at the waterway site's easily eroded, so you have to take that into account. It's going to be constructed with a parabolic shape. What top width and depth are required? And we're going to ignore freeboard at this point to keep it a little bit simpler. Okay, you've got some choices. It could be 20 feet wide and 2 feet deep, 18.5 feet wide and 1.1 feet deep, 15 feet wide, 1.5 feet deep, or 12 foot wide and 0.6 feet deep. Okay, first you got to look at permissible velocity. You've got a Kentucky bluegrass on a 3% easily eroded soil. That takes up to 5 feet per second. Let me back up here and show you exactly where that comes from. You've got easily eroded soils. You come down, you find Kentucky bluegrass. The chart has meters per second and then in parentheses feet per second. And in that particular case, and you're under 5% slope at 3%, it's easily eroded soil, it can handle up to 5 feet per second. So you're going to have to make sure that whatever channel you put together for the conditions of the design storm, it will not exceed 5 feet per second. Okay, resistance to flow. Kentucky bluegrass. Again, we come down to find Kentucky bluegrass. Good stand headed. That's when it's unmowed. It's got a C resistance. And if you come down here, you find when it's cut to a 2-inch height, it's got a D resistance. Now here's the table from the engineering field manual. So we said we had 60 cubic feet per second, a velocity of, in condition number 1, of 5 feet per second. So let's see what we got. 60. And we come along here and find that B1 of 5 feet per second, and you end up with a top width of 8.5, 1.1, and the reason it, and then we've got a B2 comes out at 4.5. That's a suitable condition. Now, would other ones work? Anything below this would work, but they would handle a much higher flow and they'd be bigger than they would have to be. So this is the one that handles the exact flow that you're talking about at the maximum permissible velocity for stability. So this is one of them that would work. You could argue, well, this 22.71 only generates 4.5. That'd be fine, but it would be bigger than it has to be. So this is actually the optimal one. And that's essentially how you do it. All right. Questions on the open channel or the grass waterways, vegetative waterways? And then just open it up to questions on anything. Slope of 0.5 when I was talking about discharge. On which problem, remind me? Okay, let me back up. Okay. Okay, let me look here quick. All right. Actually, S in that case and see here is where things get messy because we're talking about different situations. Let me ponder how this comes out for a second. Because I probably skipped some steps. Let me back up to an equation here. Let me show you why. Because there's an equation for S. Remember, curve number was 80. Okay. Combination of S and P. Let me back up one more. Potential maximum retention after runoff begins in inches. Okay. See, and if the curve number is 80, I'm just going to back calculate here for a second because now you've got me curious where that came from too. I'll walk you through it here in just a second as soon as I satisfy myself that I know what I'm doing. Yeah. Okay, here's where it comes from. If you take this equation, the curve number equals 1,000 over 10 plus S. Curve number was 80. You solve for S. So in this case, you've got 80 equals 1,000 over 10 plus S. So take the 80, it would go to the denominator under 1,000. You'd take the 10 plus S, it would be over here. So S would be equal to 1,000 divided by 80 minus 10. And if you do that calculation, 1,000 over 80 is 12.5 minus 10 is 2.5. That's where it comes from. That's a good question because I had to think about that, and that's probably something I should add to that slide to do that back calculation so you can see where it comes from. Because, I mean, S is an assumed, it's kind of a trade-off between the two. S is an assumed parameter that is dictated by the curve number, but yet the equation, the original equation, has S in it as a conceptual number or as a conceptual parameter. So, but that's where it came from. I was worried for a second that I'd messed that up, but that's where it came from. Any other questions about anything? In fact, I'm going to write myself a note to make that change in case I use that same presentation again. Okay. Okay, I hope that helped. Try to get you through some more of this. I don't remember the exact date. I've got one more of these that's going to be on essentially soil and water management. We'll deal with drainage and irrigation and essentially building upon the fundamentals that we talked about last time and some of the stuff we talked about this time with the just how you start to manage things. So there's one more coming. I'll have to remember to upload that one early because it's where this one, if some of you who are on really early was still seeing this uploaded so that I could share it online rather than sharing my desktop. This one was about 1 megabyte presentation. The next one, because it's got so many charts in it and pictures in it, is about 6. So I'll have to remember to do that a little bit earlier. Any other questions for tonight? Oh, because I volunteered at one time to do 3, and nobody's taken them away from me. Um, I don't know. Part of it was we realized that we were trying to cram way too much stuff into just a couple of presentations. And so we coordinated and built it out into 4. And then Dr. Motar does so much in his erosion and sediment presentation that, to be honest, it should probably be a couple of them as well. And we just kind of fell into this pattern. So, plus I'm theoretically retired. I'm really not, but so I have more time. It seems like, in some ways, to be honest, since I'm my area of expertise through all the years was erosion and sediment control, I almost wish I was teaching the one that Rabia's teaching, but that's okay. He does a nice job with it. So, anything else I can help you with? Let me go back to the beginning for a minute. Forgive me for running through these quick, but if you run into questions and you just need, you know, a quick answer, go ahead and send me an email. I'm actually still at U of I helping them with advising undergraduates in engineering, so I'm on that email all the time. Go ahead and send me a note. If I can point you at a reference or something that would help you out, let me know. And if you're at the ASABE meeting in Orlando, come say hi. I'll be working with some of the ABET presentations and in those particular meetings. If you've gotten your questions answered for tonight, that'll be enough for tonight. And I'll see you, I think it's early March, if I remember right, when I get to do that last one. So thanks, everybody.